Talk to you about, use the right terms here, nano-computational pattern recognition systems. It's probably a little better.
That's good. Thank you. Before I begin,
Turn the lights down.
yeah, if we could get that dimmed just a little bit. Before I begin, I'd just like to thank the Atlantic Nano Forum, more specifically Chad Weiland over there, for organizing all of this. Thank you. By the turnout, doing a great job. Also, my good friend Henry Becker introduced me to Chad, and everybody in the audience. Every time I've had a chance to present, I've come away a little more informed and a little smarter because of it. Mostly because of the questions that are asked. If you could save the questions until the end, I have a pretty long presentation, and just to get through it so we have enough time. Last year was the first DARPA Grand Challenge. For those of you unfamiliar with the DARPA Grand Challenge, it's somewhat of an epic robot race across the desert. The task is to create a vehicle that navigates itself 150 miles across the desert in about 10 hours. Now, the results of last year's DARPA Grand Challenge was more or less what I expected, actually a little better than I expected. One team made it 7.36 miles, Carnegie Mellon's red team, and that was amazing to me, actually, that they were able to make it that far. That's because the task of navigating or having a robot navigate itself, you have to have information about the environment. It has to decipher the structure of what's around it. You have to know where the road is, you have to know where it turns, you have to know whether a bush is actually a rock, or whether that rock is a puddle, or whether it's a rabbit. You have to be able to compute tremendous amount of information, of very ambiguous and noisy information. So it's largely a problem of pattern recognition, finding what's out there quickly. If I was amazed at the first DARPA Grand Challenge, I was astounded by the results this year. Not but, about a month ago, 5 teams crossed the finish line, and all but one of the 23 finalists beat the previous record. Now, this is astounding to me, but what I'd like to point out is that this tremendous progress that took place over a period of about a year didn't have a whole lot to do with smaller, faster transistors. It had a lot to do with some very clever people specifically trying to solve a problem. And I think that's, for me, the lesson of nanotechnology is giving us the ability to very intelligently solve some specific problems. And that's more or less what I've set out to do. So rather than asking the question, can we solve the problem of pattern recognition, perhaps we should be asking ourselves, can we solve the problem and fit it on a chip the size of a fingernail and power it with a watch battery? How can we turn a rack of 10 Pentium processors and a host of sensors and a generator putting out about 1 kilowatt into something a little more like this? This is from the movie AI, by the way. Now, I think this is possible. Actually, I know it's possible because biology has solved this problem for millions of years. But there's a little miscommunication about computational power and brain power. And to point that out, I found a quote from IBM's Big Blue R&D director, Paul Horn, in Business Week. And he said, "A PC today has the brain power of a lizard. In 20 years, it'll have the brain power of a human being." Now, if he said computational power, I probably wouldn't be picking on him. But he said brain power. And so I did a little homework. I was trying to find how much energy a lizard's brain consumes. I couldn't find that. So what I found is that it weighs about 0.08 grams. And we know that a human brain is 1,300 grams. It consumes about 20 watts. So using those conversion factors, comes out to 0.001 watts, which is 20,000 times more energy efficient than one of the Pentium processors on board Stanford's Stanley robotic land vehicle. When power comes into the equation, traditional computing doesn't even come close. It's not even a runner-up. It's a challenging problem, and doing it efficiently is the challenge. And biology has solved that problem. So the goal of Knowm Tech, my goal, is to solve this pattern recognition power problem. And the way that I'm trying to do it is actually build a neural system from the bottom up, neuron for neuron, synapse for synapse. If you can build a one-to-one mapping, rather than simulating a neural pattern recognition system, you actually build it. If you can do that, you'll be able to create a system that is as efficient as a biological network, or very close. And you could run it a lot faster, and it would be more powerful. So, well, solving the problem then is just half the problem. If you want the solution to fit on a chip, you want it to be scalable and power efficient and cheap and adaptive and all these other things that go along with a very robustly solved problem, then it has to have all those qualities too. It can't be a huge rack consuming a kilowatt, especially if it's for autonomous vehicles. And so for me, these last 4 years, the question has been, is it the algorithm or is it the architecture? If you look at a brain and you ask that question, it's very clear that it's both. The algorithm is the architecture. So if you go too far down the algorithm direction and you come up with a pile of equations, and then you turn around and try to implement in a computing platform, FPGAs or microprocessors, they won't be a very good match, and you'll end up consuming about a kilowatt. If you go down the architecture route and you come up with a very wonderful, fast nanoelectronic system, turn around and try to find an algorithm and match them, and they won't be very efficient. So what I've been trying to do for the last 4 years is solve the problem from both perspectives at the same time. And it's been very slow, but it's starting to bear some fruit. So this is what I'd like to talk to you today about. I'll try to talk as generally as I can, take you in the best way I know how, from particles on the surface of a chip to scalable, self-assembling, robust pattern recognition chips. Most nano talks kind of focus very, very narrowly on something, and I'd like to give you, as best I can, a picture of how we can go from particles all the way up to a chip. I'd like to show you how, by looking at both the algorithm and the architecture, you actually can solve problems by bouncing one off the other. You solve an architectural problem that leads you to an algorithm solution, and vice versa. Good news is that I'm going to try to present this all. The bad news is it's very interdisciplinary. I've combined aspects of computational neuroscience, something called plasticity and feedback systems. So it's very hard to get across, and it can be very confusing. So if you have any questions, please take note of them, particularly how I use a word. Sometimes that gets confusing. And if you'd like more information about this, I'm going to put this presentation along with the video on my website, knowmtech.com/ANF/index. So it all starts here with a particle floating around in a solution and is jiggling around because it's experiencing random bombardments from the liquid. Brownian motion. Einstein described it very well, and it's actually one of the real times people finally said, okay, there's atoms, we get it. So it's jiggling, we know this is nano. If you add some electrodes and you charge them up, the particle is going to align in the direction of the field. And if it's homogeneous and the particle has no charge, that's about all it's going to do other than jiggle around. If you add some charge, it's going to feel a force, and it's going to go to whatever electrode given by the electric field. You can do something more interesting. You can bend one of the electrodes. You can make it sharp, create an inhomogeneous electric field. So now the particle not only feels a torque and aligns with the principal axis of the particle aligns with the field, but it'll be attracted to areas of increasing energy density. So it's going to pile up at the corners. And before I discuss how I think you can use this as synaptic connection, review very quickly CMOS. What we have here, just your silicon crystal, it's doped and has charge carriers. And what makes it work is that you have an accumulation of charge carriers. You attract them all to a region, and that accumulation lets the thing conduct from the source to the drain. So a Knowm connection is similar in concept, although vastly different in fabrication. Rather than source in the drain, you have a presynaptic, postsynaptic electrode. And you have nanoparticles floating around in the solution, experiencing Brownian motion. In fact, activate the electrodes, that is, you put a voltage across them. They're going to be attracted to the areas of increasing energy density. They're going to be attracted to the corners, and they're going to slowly start building up a connection. And over time, that connection is literally, it's a little nano resistor, and it's going to decrease the resistance of the connection. It's going to build up. And if you take that voltage off, they're going to dissolve away. This video is available at dielectrophoresis.org. This is DNA being aligned under this process I just described. You turn the field on, in this case an alternating electric field. Distance is about 1 micron, and via dielectrophoresis, positive dielectrophoresis, gets drawn in, the field goes off, and it dissolves away. I'd just like to point out this notion of moving charged neutral particles around via dipole-induced forces has been known since about the mid-60s. Dr. Pole discovered it, and since then it was slow to catch on because the fields necessary to generate the forces to overcome Brownian motion are the result of basically microfabricated electrodes. And until you could have a really sharp corner, you couldn't really overcome these forces and generate enough force to maneuver them. The force has been used, actually exploded over the last couple of years, mostly for trying to move DNA around. But it's just, they've gone nuts with it, and there's a few textbooks out now. And so what I'd like to just demonstrate here, it's not a matter of whether or not you can attract these nanoparticles to a gap. That's known. The problem is, how do you use this? It seems like we have an incredibly valuable system here. We can attract nanoparticles to a specific region, and we could control it with electric fields, which means we could possibly control it with CMOS electronics underneath. The question is, how do you do this? What I thought of was, what if you use this as a dynamic connection? I actually tried to emulate a synapse. But of course, how do you work with these particles that just don't stay put? So the goal, by the time you leave here today, I hope you'll understand how we can do something along these lines. We can take particles floating around in a solution, and we can selectively attract them to certain electrode gaps and not to others. And in the process, form little nanoresistors that act as synapses in an information processing system for recognizing patterns. Just to be clear, this is an extraordinarily complicated proposed electronic device. To start off, you have Brownian motion, so there's this inherent randomness to it. Quintessential randomness. Then you have conduction through the liquid and also through the particles, which causes electrothermal forces and convection, sedimentation possibly from gravity or external accelerations. You have interparticle attractions. You have colloidal properties, zeta potentials, heat capacities. It's unbelievably complicated. But the same thing that makes it very complicated could also make it very simple. Now, if you imagine the connection not being a long filament, but being arranged over exactly the opposite dimension, so that a connection is actually a lot of little connections. And if you look at an area across an electrode, and it doesn't have an electrode, doesn't have a connection bridging it, you could say, what's the probability, given the electric field at that region over time, that a connection will form? And alternately, if a connection is formed, you could say, given Brownian motion and in the heat, what's the probability that connection will break? And if I know those two probabilities, then I can start building up a system and using this. For those of you in the audience who are familiar with molecular switches, one question that might pop into your mind is, well, if you've just taken this complicated system and expressed it in terms of these probabilities, why couldn't you just use a molecular switch? They have 2 or more states, and conducting and non-conducting, and there's probabilities that they'll be moved into one state or another. And the answer is you could, but they'd have to be unreliable. They'd have to be volatile, or I wouldn't be able to use them in the system that I'll describe to you today. In other words, if you applied a voltage and set these molecular switches, they would have to be able to spontaneously decay to their ground state without the influence of an external electric field. That's very important. So I'm sure one day we'll have molecular switches coming out of our ears, and we'll be able to find a molecular switch with just the right properties that we need, these transition properties. Because we need them if we're going to use this as a synapse. That controls the learning rate of the network. So we need control over these transition probabilities. For the meantime, we can actually exercise a lot of control over the transition probabilities of particles in a solution, because we do have control over a lot of the parameters of that system. We have parameters of the solution itself, the viscosity, the permittivity, the heat capacity. We have different particles we can use, different materials, different permittivities, different sizes, which affects the force that it feels. So a bigger particle is going to feel a bigger force, which is going to increase the probability that the connection is going to be made, vice versa. Almost every parameter we actually have control over, so we can adjust the system and create these transition probabilities that we need in order to build a neural system. So this is the idea. We're going to take these nano connections, and we're going to make synapses out of them, and we're going to try to build a neuron with CMOS. And this is your standard picture of a neuron. It's about as simple as it can get. 2 inputs, 2 synapses that weight the inputs, W1, W2, and Y is the total activation. It's going to sum up a signal from the 2 inputs, given the attenuation from the synapses. Before I go any further, this is a cause of confusion. It's kind of unnecessary confusion, but nonetheless. When I plot these points, I'm plotting 1 and -1. That's important because 0, the notion of state is very important in the system. Whenever you multiply 0 by anything else, you get 0. And for some reason, that causes undue confusion. So anytime you see these points, 1 and -1, not 1 and 0. So we have a neuron that has these 2 inputs. We're going to process binary data. For all practical purposes, information anywhere, you're going to transmit it, if you're going to store it, it's going to be binary. It's not going to be analog. 2 inputs, 2 states, 4 possible patterns. And we look at this over time, and we get a picture of how noisy those data points are. The bigger that cloud, the more noise there is in the system. If we would like to look at this neuron in this data space, we can solve for the point where the neuron makes a decision. If it adds up the input multiplied by the synapses and you end up with positive, then it's sort of like the neuron saying yes. And if you add it all up and it's negative, it's like it's saying no. And if you solve for 0, you find the decision boundary and you plot that. And everything on one side of the decision boundary is going to be positive or activated, and everything on the other side is going to be negative or not activated. You're solving for the point of decision. So when I plot this line, this is a representation of the synaptic weights. So we can make our first observation here. Given that we would like to classify information with a neuron, given that this decision boundary is representation of the weight values, in order to achieve all possible classifications or orientations, we're going to have negative synapses. The synapses are going to have to possess a negative state, which is not something people normally think about. They think about a connection that attenuates, but not a connection that actually has a state. A synapse has a state means that you're dealing with polarities. You can have a positive input and negative input, 1 or 0. And the connection having a state means that if it's negative and the input's negative, it's going to flip it. It's just the rules of multiplication. So if we can encode that state transfer, then we can work with the synapse as a neural processing system. It has to have a state. To do that, we're going to take 2 of these nano connections formed by the dielectrophotic aggregation of nanoparticles, and we're going to call one the positive, one the negative. If the positive is greater than the negative, then the connection's positive. If the negative's greater than the positive, then it's negative. So now we have magnitude and state, and that's important. The side view you see here, this is the basic setup that we're dealing with. The red is the presynaptic electrode, blue is postsynaptic, and underneath we have CMOS that's powering the system. It's going to be applying feedback to the system. For those of you with an electrical engineering background, it's just a voltage divider. And the voltage you're going to see on the postsynaptic electrode is a reflection of the value of the synapses. So we can make another observation here. Out of all possible orientations, out of all possible synaptic values, given that there's just these 4 input patterns, there's only 4 states that we really care about. And those are the states that divide these patterns up into 2 halves. There's only 4 ways you can slice this, because going through one of these data clouds, one of these data points, doesn't really make a whole lot of sense. So we need to find a way, we need to find a system so that these are the only states that are allowable, these 4 states. These are the independent component states of the system. If we can do that, we can start to build up a processing system. So not to get too abstract, the idea here is we have a neuron, which I'll talk about shortly, which is subsurface CMOS circuitry. It's powering the postsynaptic electrode, here blue, and then presynaptic electrodes on the surface. And at the intersections, particles are going to be attracted to the electrode gap. And we're going to figure out a way so that we can get the particles to stick in an electrode gap that we want. Now, those 4 orientations that I showed you were quite simple. It's basically one of the synapses is positive or negative, and the other is 0, which means that the stable states are just, well, a connection on one and not the others, or a connection very much stronger on one than the others. So we have to design a system to do this. To give you a metaphor, suppose you had 4 people, and they had to give an answer, yes, no response. Well, they would all have their individual yes, no response, and as a group they'd give you an answer. But with one caveat. People have different importances. So you can imagine that maybe there was a leader of the group, and they had a lot of importance. And so if they said yes or no, then that was really the group response. Now if the individuals, or the other people in this group, actually supported that leader, gave them positive feedback, then we'd create a stable situation. There can only be 4 leaders. So if we do this, if we apply positive feedback, we could create these stable states. This little animation you see on the corner, this is weight space, 2 synaptic values. If you just initialize them randomly anywhere, they're going to fall into 4 attractors. Those attractors are those stable states. There can only be one leader. There's 4 synapses, and one of them is going to win. Now this is actually called plasticity. In computational neuroscience, there's a rule there's a bunch of rules for how a connection between 2 neurons changes as a function of how it's used. And it turns out that if you iterate these rules over and over again, you can extract statistical information about the data stream that's being processed. Now, I stumbled across this rule essentially by accident and went digging around, and it pops up in a lot of places. If anybody's familiar with support vector machines, this rule essentially maximizes support vectors. If your background is in mathematics or statistics, this is finding the independent components of a data stream by minimizing a kurtosis objective function. But more simply, this is just positive feedback. So the goal here is to use plasticity, positive feedback, to reinforce these connections so that only certain states are stable. So let's just look at a neuron with only one input. It has a positive input, negative input. Suppose that that connection was slightly positive. And we look at the voltage built up over time. It's going to look something like this. Slightly positive, so it's going to go up like this. If the connection was, if R2 was much less than R1, we get something like this. Now, the force that these particles are feeling is a function of the energy density. Since the geometry doesn't change on this chip, it's a function of the pre- and postsynaptic voltages. higher the voltage difference, the greater the force that they're going to feel. So if we ask the question, how many nanoparticles are going to be attracted to this gap, that's a function of the force that's felt by them and how long it's felt by them. So if we look at the area, say this is positive, the positive presynaptic electrode, negative. If we look at the area between them, that's an indication of the total accumulation of probability that a connection is going to be at that gap. So that's another way of saying the amount of update, the amount of particles that this connection is going to receive over this increment is related to this area, where in this case red is positive connection, blue is a negative connection. So if we look at this as varying values of activation, this is only one input, so the activation is given by this resistance. As this resistance goes down, the conductance goes up, we see that it faster and it more quickly saturates. And so the amount of accumulated update over time actually goes down. So this is actually negative feedback. It's exactly opposite of what we want. But it's not surprising because we haven't actually used any feedback from the CMOS yet. If we separate this into two stages, for those of you familiar with electrical engineering dynamic logic, you have two-phase pre-charge evaluate. So in this phase, we evaluate the connection. It evaluates positive. And in the second phase, we apply positive feedback. And so we always get this incremental quanta of update. And as the connection gets stronger and stronger, it's going to go to 0. Now, this connection is the sum total of both the positive and negative contribution. So the difference between the two is the actual update. And you subtract them and you get basically the rule that we want, with one added feature here, and that is you have this offset. No matter what, this connection receives an accumulation. It receives a probability that connections are going to be attracted to that region. But if this connection didn't break, over time, both of those connections would receive equal accumulations, and they'd saturate. And both connections would be the same. So in other words, the connections have to break. If they don't decay, if they don't break, if Brownian motion doesn't move them around, then the system won't work. So the circuit to apply positive feedback is quite simple. You integrate the signal, and then positive feedback, for those of you in electrical engineering, that's just a voltage keeper. And you apply basically an inverter to flip it. I call this the flip-lock cycle because you flip one of the inputs and you lock the other input. So this is your neuron. This is the circuitry required to apply positive feedback to the synapses. And as long as it follows this evaluate feedback cycle, what's going to happen is those synapses are going to be locked into attractor states, and they're going to stay stable. As long as this thing processes information, those connections are going to reinforce each other and continually repair themselves. Can't talk too much about building bigger neural systems out of it. More specifically, things called lateral inhibition and whatnot. So you have your basic neuron, and it's implemented in CMOS circuitry. And you have your postsynaptic electrode, which integrates a signal, and presynaptic electrodes, differential electrodes. And so that's your standard notion of what a neuron is. And you can array them together and build up groups of these. The key here is that this neuron is extracting the statistically independent components of a data stream. Independent components are sort of like saying, well, let me find the alphabet of if I know the alphabet, then I can build up a system with it. It's with using independent components, you can then build up computational systems and classification systems and whatnot. So the first thing we can do, for those of you with any background in digital logic, you know that you can represent any logic function in a way called the sum of products, which requires that you invert some inputs and then you AND them, and then you OR them. So it shouldn't be too surprising that if we have these neural nodes and each one is locked into an independent component state, which will pass or invert one of its inputs, that acts as the inverter, and that state can be changed, then by configuring the states of these neurons, you can configure the logic function. You just have to add some logic. Now, you're not going to get universal logic with this gate. It requires something called a bias, but I'm not going to go too much into that. If you like more information, talk to me afterwards. In any case, you have these states, and by configuring each state leads to a different logic function. More exciting than reconfigurable logic is pattern recognition. So one thing, there's a lot to this, but basically we have a neuron, and it's an independent component state with binary full basis set. Those independent component states are going to represent a connection that is either passing or inverting just one of the inputs. So it's sort of like a router. It's passing or inverting one of its perhaps 32, 64 inputs. Now if we create an ensemble of these where each one is locked onto a specific electrode, then depending on its state, it's either going to be positive or negative. It's going to invert a signal or not invert a signal. So if the input coming in agrees with the neural state, the output of this neuron is going to be a positive quanta of charge, which is built up on its electrode here. If the input does not agree with the state, say if the state's 0 and the input is 1, then you're going to get a negative quanta of charge. Now, if all of these neurons output that charge onto an electrode, what you're going to get is a measure of the recognition of the input pattern with the neural states. So you have a stored state in these neurons, and you have an input pattern, and if the pattern matches, then you're going to get big quanta of charge, all positive, which is going to express itself as a voltage on a common electrode. And as the pattern doesn't match, then you're going to get less and less of a voltage. But there's a problem with using analog voltages on highly integrated chips, and that is they're subject to a lot of noise. The problem with this pattern recognition is that we need a measure of how good of a match it was. And we need to get that information out, otherwise we don't really have a good basis for designing these systems to make decisions on patterns. But if we turn that analog signal into a digital signal, we'd use up a lot of wires, a lot of circuitry. But if we insisted on using an analog signal, then it would be subject to noise, and it would be very hard to get that analog signal out of this incredibly integrated system. So we can do something different. We can apply positive feedback again. And positive feedback, if you want to know the outcome of a system iterated on itself, you can draw a diagram like this. It's called a cobweb diagram. So if it starts off, say, very close to 0, it's going to take a long time to saturate. If it starts off, say, much closer, then it's going to take less time to saturate, just like a ball rolling down a hill. If it starts off right balanced at the top, it's going to take a long time to fall down. If it starts down at the bottom, it's going to take less time. So if we apply positive feedback and we measure the time it takes to saturate, we can convert that analog signal into a time signal, a time interval. The greater the match, the shorter the time. So now we have these circuits that encode pattern recognition accuracy as a time interval. But this introduces another problem. We have a highly integrated chip, and we need to get that time interval out of it. And in order to do that, we'd have to have these circuits exactly the same distance from each other. So how do you solve that problem? Well, we can take some inspiration from nature. If there's any structure that nature just screams at you, it's that of a tree. So if we imagine that these leaves here were actually pattern circuits, and each circuit received this input pattern, and each pattern circuit has its own internal state, which represents a representation of a pattern, then the better the pattern match, the sooner it's going to activate. And it's going to send a signal down this fractal tree. And if everything's even here, then the distance from every single pattern circuit to the trunk is exactly the same. And if you keep track of what direction you turn on the way up here, it has its own unique address. It turns out this pattern can be mapped really nicely onto a two-dimensional surface. So imagine we had all these pattern recognition circuits all over a chip. And we had this sort of fractal distribution output layer. Then maybe this pattern recognized or this circuit recognized the pattern first, and it sent a signal down. Every time it makes a turn, it adds a bit to its address electrodes. Takes a right turn, it adds a 1, takes a left turn. And once the pattern comes out, it's the address of the pattern that recognized, it's the address of the circuit that recognized the pattern first. And the time that it took that to occur is a measure of how accurate the pattern match was. So we can encode both what was the best match and how good of a match it was. Turns out everything wraps up very nicely in itself. What you have is essentially a 5-metal layer process. You have a distribution layer along the surface of the chip where the pattern is demultiplexed and sent out, highly parallel over the surface. You have connections forming between presynaptic, also called axonic, and the dendritic electrodes. Via one via to the active portion of the chip where the CMOS circuitry is held that provides a positive feedback which keeps everything stable. Metal 1, metal 2 is used for various functions, the teach, the clock, interconnect. And the output layer is where the signals get broadcast out. And because everything's highly symmetrical, same capacitances, same distances, the timing interval gets essentially conserved, and you can represent that analog measure of accuracy by encoding the time, and you can get that out of the chip. And notice so far everything here is 100% parallel, which means if we could broadcast this pattern simultaneously across the surface of the chip, we could have recognition events occurring simultaneously all over the chip all at once, so that maybe 1 million circuits are all trying to see if that pattern is indeed the pattern that matches their internal state. Well, that pattern is a fractal architecture, and fractal architectures are naturally scalable. You put 2 and you form the same structure. You put 2 of those together, you form the same structure. So you can imagine these are router circuits, and I haven't talked at all about the router circuits. Combine 2 of these, I call them fractal memory chips, with a router circuit, and you get yourself a bigger fractal memory. So on and so on. So you can imagine each chip is now one of these memories, and they're combined with these router circuits. And you can combine 2 chips into 4 chips, 4 chips into 8 chips, on and on and on and on. So when you want to recognize a pattern, you can send that up through the router circuits where it gets unwoven, it gets demultiplexed and broadcast over the surface of the chip. And you have simultaneous pattern recognition over the entire chip. And the first signal to get back to you is the best match. And the time that it takes is how good of a match it is. So in other words, you could scale this system as much as you want. And the time it would take to find the best match of a pattern wouldn't change at all. The only extra time is the time it takes an electrical signal to propagate through this, which for all practical purposes is not a whole lot. The limiting factor is the integration of the synapses. So you can only say that because it's architecture. I couldn't say that to you with a straight face unless this was 100% parallel. And in fact, this architecture was a result of trying to solve this problem of stability and actually encoding a recognition. So solving the problem led me to this. As far as the applications, it's all about just one question. That's it. Given the sequence of 1s and 0s, what is it? If you look at an object, there's something not arbitrary about it, the structure of it, the corners of it, how it's shaped, and there's something completely arbitrary, which is the name that we give it. And what we're trying to do is map that structure to a name. In other words, an address on a chip. So the applications are really all over the place. Speech recognition, one of one of the largest. What you're trying to do is you gather information about a pattern, and you're trying to say, what word is this? And you have a humongous vocabulary system. Well, if you had each one of these pattern recognition circuits representing a phoneme, well, the best match comes to you first, and then alternately you could have each pattern recognition circuit representing a word, and the first retrieval from this memory is the best match. This isn't a mechanism for building universal computers, not at all. It's simply about speeding up the process of pattern recognition. This is going to be used in combination with computer architectures. And what I've shown you here doesn't really completely solve classification pattern recognition problems. You're going to have to use a number of these chips, and you're going to have to use them in concert with standard computer programming to start making the decisions. It's not enough to just say what it is. You have to do something with it as well. And so it's really the synthesis of the two that's, I think, really going to be quite powerful. With that, I'd just like to conclude. I've shown you how a particle can be used to build up a connection, and how two connections have to be used to encode a synapse with both a magnitude and a state. Shown you how positive feedback can be applied via subsurface CMOS circuitry to implement a neural node, a neuron, that has distinct states. Now those states can be configured to implement any logic function. And how those states, whenever you take an ensemble of neural nodes, can be used to implement pattern recognition. Showing you how the problem of determining how well of a pattern match you have leads you to a problem of representing an analog signal, and how that turns into temporal encoding of the analog signal, and how that temporal encoding leads you to a fractal architecture, because that's the only architecture in which the distance from every point for every pattern circuit is the same all the way to the exit point of the chip. And in turn, I've shown how the fractal architecture leads to a indefinitely scalable pattern recognition architecture, simply as a matter of its design. It's already scalable because it's a fractal. Before I conclude for good, I'd just like to mention a few things. The first question that comes up is, well, this connection is very slow, so how is it good? And that's the entire point. It's slow because it's used in a system that learns. And learning and fast are not equivalent. You don't flip this bit, you push it gradually. It's an accumulation of little incremental updates over time, and that's what makes us powerful. We're taking a system and we're using physics of the solution to implement the dynamics that we need. We're not just flipping bits on and off. And also, there's no inherent reason that I can see at the moment why we can't build this system. Subsurface CMOS circuitry, the synapses are going to have to form between the fourth and fifth metal layers, which means we're limited in dimensions because we can't have as small electrode widths as we could on the first metal layer. But that leads to incredibly powerful systems. So with that, I'd like to thank everybody for paying attention. And if you have any questions, please do ask.
Any questions, please? I have a question for the audience. Is anyone else's brain really hurt this?
I was worried about that, sorry. I didn't mention at all teaching. That's
all right. Well, I guess that's it. Let's have another round of applause and thank you.